In this module, we shall discuss about the regression analysis. Unlike correlation, which studies the relationship between two variables, regression analysis involves prediction of average value of dependent variable on the basis of fixed values of the independent variable. The simplest form of regression analysis is a two variable linear regression line given by y is equal to a plus bx. Here x is the independent variable, y is the dependent variable, a is the intercept, b is the slope of the line. A regression line tells us the estimated effect on y of a change in x measured by the slope. The slope measures the amount by which y changes corresponding to a unit change in the x variable. For example, P is equal to A minus BQ shows the relationship between price and quantity demanded of a product. A two variable regression model or the population regression line, which is PRF, is generally given by yj is equal to beta O plus beta 1 xj plus ui. The population regression line is estimated using a simple regression function SRF given by y hat I is beta hat O plus beta hat 1 xi plus u hat I. Here beta hat O is the sample intercept, beta hat 1 is sample slope coefficient, and u hat I is the residual term and assumed to be normally distributed with mean 0 and standard deviation sigma. These parameters are the estimates of population parameters. However, the two variable analysis is often inadequate in the sense that it is limited only to two variables, does not take into account other factors that are affecting the dependent variable. For example, quantity demanded of a product is not just dependent on its price, but depends upon price of related goods, income of the consumer, type of good, etc. To take into account such factors, we extend our regression analysis to cover models involving more than two variables known as multiple regression analysis. In short, under multiple regression, additional factors are allowed to enter the analysis separately so that the effect of each can be estimated. It solves the problem of omitted variable bias associated with simple regression, as all the variables affecting the dependent variables are taken into account. For the sake of simplicity, we will restrict ourselves to a three variable regression with one dependent and two explanatory independent variables. After studying this module, you shall be able to know the concept of multiple regression, learn how to estimate a multiple regression model, know the concept of restricted least square. A simple linear regression model is not adequate for modeling many economic phenomena because it is necessary to take into account more than one relevant factor in order to explain an economic variable. The multiple regression analysis is an extension of simple linear analysis. In the Keynesian consumption function, disposable income is the only relevant variable. Consumption is equal to beta 1 plus beta 2 income plus mu. However, apart from income, there are other factors such as wealth that may be considered relevant in analyzing consumer behavior. By including wealth, we will have a model with two explanatory variables. Consumption is equal to beta 1 plus beta 2 income plus beta 3 wealth plus mu. The previous model is clearly insufficient for economic analysis. It would be better to use the well-known Cobb-Douglas model that considers two inputs, labor and capital. Log output is equal to A1 plus A2 log labor plus A3 log capital plus mu. Similarly, while analyzing costs, we use a cubic function, which leads to the following econometric model. Cost total is equal to beta 1 plus beta 2 quant prot plus beta 3 quant prot 2 plus beta 4 quant prot 3 plus mu. Thus, the example highlights the need for using multiple regression models. Three variable regression model. The three variable PRF is yi is equal to beta O plus beta 1 x1i plus beta 2 x2i plus mu I, where y is the dependent variable, x1 and x2 are independent variables, mu is stochastic error term, and I is the ith observation. Beta O is the intercept term, gives the mean effect on y when all the variables are excluded. Beta 1 and beta 2 are partial regression coefficients. We assume the same conditions as assumed under the simple regression analysis. That is, zero mean value of mu I, expected mu I divided by x1i, x2i is equal to 0 for each I. Second, no serial correlation, covariance mu I mu j is equal to 0 for I equal to j. Homoscedasticity, variance of mu I is equal to sigma squared. Zero covariance between mu I and each x variable. Covariance mu I x1I is equal to covariance mu I x2I is equal to 0. The model is correctly specified. No multicollinearity, no exact linear relationship between the x variable. It implies there exists no set of numbers alpha 1 and alpha 2, not both zeros, such that a1 x1I plus a2 x2I is equal to 0. If such an exact linear relationship exists, then x1 and x2 are said to be linearly dependent. Given these assumptions, we get the conditional mean value of y conditional upon the fixed values of x1 and x2, that is expected value of bracket open yi divided by x1I x2I is equal to beta o plus beta 1 x1I plus beta 2 x2I. Partial regression coefficients. As pointed earlier, beta 1 and beta 2 are partial regression or slope coefficients. Beta 1 measures the change in the mean value of y per unit change in x1, keeping x2 constant, and beta 2 measures mean value of y per unit change in x2, keeping x1 constant. Ordinary least square or OLS estimation of partial regression coefficients. Here we extend the OLS estimation of a simple two-variable linear regression model to incorporate three variables. Consider the sample regression function SRF corresponding to PRF. Yi is equal to beta hat O plus beta hat 1 x1I plus beta hat 2 x2I plus mu hat I. The SRF must be the closest approximation of the PRF since PRF is not directly observable. Under the OLS estimation, we aim to minimize the residual sum of square RSS into sigma u hat I squared, as the estimator so obtained will carry the desired statistical properties. That is, minimum of sigma u hat I squared is equal to sigma yi minus bracket open b hat o plus b hat 1 x1I plus b hat 2 x2I the whole squared. To obtain the estimates, differentiate the above equation with respect to the unknowns, set the resulting equation equal to 0 and simultaneously solve them. We obtain the normal equations as y bar is equal to beta hat o plus beta hat 1 x1 bar plus beta hat 2 x2 bar, sigma yi x1I is equal to beta hat 2 summation x1I plus beta hat 1 summation x1I squared plus beta hat 2 summation x1I x2I. Summation yi x2I is equal to beta hat o summation x2I plus beta hat 1 summation x1I x2I plus beta hat 2 summation x2I squared. From these equations, we get the OLS estimators of the population partial regression coefficients beta 1 and beta 2 respectively. Beta hat O is equal to y bar minus beta hat 1 into x bar 1 plus beta hat 2 into x bar 2. Beta hat 1 is equal to summation yi x1I into summation x squared 2I minus summation xyi x2I into x1I x2I all over summation x squared 1I into x squared 2I minus summation x1I x2I the whole square. Beta hat 2 is equal to summation yi x2I into x squared 1I minus sigma yi x1I into x1I x2I the whole over sigma x squared 1I into summation x squared 2I minus sigma 1I x2I the whole squared. Variance and standard error of OLS estimators. The standard errors of OLS estimators are required to form two important statistical inferences to construct confidence limit and to test statistical hypothesis. Variance B at O is equal to sigma squared bracket open 1 by n plus x bar squared 1 sigma x squared 2I plus x bar squared 2 sigma x squared 1 I minus 2 x bar 1 x bar 2 summation x1 I x2I all over summation x squared 1I into summation x squared 2I minus summation x1I x2I the whole squared. Standard error beta hat O is equal to plus root of variance beta hat O. Variance of beta hat 1 is equal to summation x squared 2I sigma squared divided by summation x squared 1I into summation x squared 2I minus summation x1I x2I the whole squared. We know that r squared 1 2 is equal to summation x1I x2I the whole squared divided by summation x21I summation x squared 2I. Therefore, variance of b hat 1 is equal to sigma squared divided by summation x squared 1I into 1 minus r squared 1 2, where sigma square is homoscedastic variance of population error term mu I. Variance b hat squared is equal to summation x squared 1I sigma squared divided by summation x squared 1I into summation x squared 2I minus summation x1I x2I the whole squared. Variance beta hat squared is equal to sigma squared divided by sigma x squared 2I into 1 minus r squared 1 2 bracket close. Standard error b hat 2 is equal to plus under root variance b hat 2. Covariance b hat 1 b hat 2 is equal to minus r12 sigma squared divided by 1 minus r squared 1 2 root sigma squared 1I root sigma x squared 2I. Also, sigma hat squared is equal to sigma u hat I squared divided by n minus 3 is an unbiased estimator of sigma squared, where sigma hat I squared is equal to sigma y squared I minus b hat 1 sigma y I x1 I minus b hat 2 sigma yi x2I. The degrees of freedom are computed as n minus 3 because while estimating sigma hat I squared, we estimate three estimators beta O, beta 1 and beta 2. Now we shall discuss the coefficient of determination. An important part of studying the regression is testing how good the estimated equation fits the observed data. The coefficient of determination R square is a measure of goodness of fit. It gives the proportion of total variation in the dependent variable explained by an explanatory variable. In simple term, it measures the amount of the sample variation in Y that is explained by X. Extending this concept to a multiple variable model, we get multiple coefficient of determination. In a three variable model, yi is equal to beta hat O plus beta hat 1 x1I plus beta hat 2 x2I plus mu hat I. R squared will measure the variation in y explained by the variables x1 and x2 jointly. Yi is equal to y hat I plus mu hat I. Considering the deviations from the mean values, we have y hat I is equal to beta hat 1 x1I plus beta hat 2 x2I plus mu hat 1. That implies yi is equal to yi hat plus mu hat I. The total sum of squares or TSS is defined as the total variation in y around its mean. It is given by sigma y squared I. TSS is equal to sigma I moving from 1 to n in bracket yi minus y bar the whole squared, which implies sigma yi squared is equal to sigma y hat squared I plus sigma mu hat squared I plus 2 sigma y hat I mu hat I, which is equal to sigma y hat squared I plus sigma mu hat squared I. On substituting the values of sigma mu hat squared I, we have sigma y hat squared I minus sigma y squared I minus beta hat 1 sigma y I x1 I minus beta hat 2 sigma yi x2I. The explained sum of squares which is ESS, is sigma y hat squared I is equal to beta hat 1 summation yi x1 I plus beta hat 2 summation yi x2 I. ESS is simply the variation of the estimated y around its mean. ESS is equal to sigma I moving from 1 to n in bracket y hat I minus y bar the whole square. Sigma mu hat squared I gives the residual sum of squared RSS. It is the amount of variation not explained by the regression equation. RSS is equal to sigma I moving from 1 to n mu hat I squared. Hence, TSS is equal to ESS plus RSS, which implies 1 is equal to ESS divided by TSS plus RSS divided by TSS. R squared is equal to ESS divided by TSS, which is equal to 1 minus RSS divided by TSS, which is equal to beta hat 1 summation yi x1I plus beta hat 2 summation yi x2I, all divided by sigma y squared I. 1 minus sigma mu hat squared I divided by sigma y squared I, which is equal to 1 minus bracket open n minus 3 sigma hat squared divided by n minus 1 s squared y bracket close. The value of r square lies between 0, which is no fit, and 1, which is perfect fit. If it is 1, the fitted regression line explains 100% variation in y, and in case it is 0, the regression line does not explain any variation in y. From R square, we can estimate the coefficient of multiple correlation R, which shows the degree and direction of association between the dependent variable and all the explanatory variables jointly. Unlike linear correlation coefficient, R is always positive. R squared and adjusted R square. R square is a non-decreasing function, the sense that as number of explanatory variable increases in this model, R squares continues to increase and never decreases. We know that R squared is equal to 1 minus sigma mu hat squared I divided by sigma y squared I. Here, sigma mu hat squared I depends upon the number of the explanatory variables. As they increase, sigma mu hat squared I is likely to decrease, and thus R square will increase. Therefore, one must be careful while comparing two models with same dependent variables, but with different number of explanatory variables. The problem can be solved if we take into account the number of explanatory variables into consideration while calculating the R squared. R squared bar is equal to 1 minus sigma mu hat square I divided by n minus k, the whole divided by sigma y squared I divided by n minus 1. R bar squared is the adjusted R squared, adjusted for degrees of freedom associated with the sum of squares. Here k is the number of parameters in the model including the intercept. It can be negative unlike R squared, which takes only positive values. In case it is negative, we consider its value as 0. R bar squared is equal to 1 minus sigma hat square. We can also write R bar squared is equal to 1 minus bracket open 1 minus R squared bracket close into n minus 1 divided by n minus k. For k greater than 1, R bar squared is less than R squared, which implies that with increase in the number of explanatory variables, adjusted R squared increases less than unadjusted R squared. Next, we shall study about the restricted least square. So far, we had discussed estimating or predicting relationship between one variable and number of related variables. One must note that there are instances when estimation of regression coefficient is subject to linear restriction and testing of linear restriction. The simplest example is the specification that one or more regression coefficient are equal to 0 or some other constant. The restricted least squares estimation method enables the use of sample information and prior information simultaneously. Let us understand the concept with the help of a Cobb-Douglas production function. Yi is equal to beta 1 x raised to the power of beta 2 2I into x raised to the power of beta 3 3I e raised to the power of mu I. Here y is equal to output, x2 is equal to labor input, x3 is equal to capital input. We can write the above equation as yi equal to beta o plus beta 2 ln x2I plus beta 3 ln x3I plus mu I. Here beta O is equal to limit of beta 1. The constant returns to scale theory would suggest that beta 2 plus beta 3 is equal to 1. This poses a linear equality restriction. There are two approaches for finding such restrictions: the t-test approach or the unconstrained regression. The equation yi is equal to beta 1 x raised to the power of beta 2, 2I x raised to the power of beta 3, 3I e raised to the power of mu I can be estimated without considering the linear restriction. Here we attempt to test the presence of linear restriction after estimating the unconstrained regression. The steps are as follows. Estimate the parameters beta 2 and beta 3 through OLS. Use the t-test to test the hypothesis or the restriction. Under the null hypothesis that beta 2 plus beta 3 is equal to 1, the t-variate is t is equal to beta hat 2 plus beta hat 3 minus beta 2 plus beta 3, the whole divided by standard error of beta hat 2 plus beta hat 3, which is equal to beta hat 2 plus beta hat 3 minus 1, the whole divided by under root variance beta hat 2 plus variance beta hat 3 plus 2 covariance beta 2 beta 3. If the computed t value exceeds the critical value at chosen level of significance, reject the null hypothesis of constant returns to scale, otherwise do not reject it. The F-test approach, restricted least square. Under the restricted least square procedure, we incorporate the restriction in the regression itself and then carry out the estimation procedure. This can be applied to models with any number of explanatory variables and with more than one linear restriction. The F-test is a device for testing differences in the sum of the squared residuals obtained by estimating a restricted model and an unrestricted model. Beta 2 is equal to 1 minus beta 3 or beta 3 is equal to 1 minus beta 2. Using any of the above equalities, we can write limit yi is equal to beta o plus 1 minus beta 3 limit x2I plus beta 3 limit x3I plus mu I, which is equal to beta o plus limit x2 plus beta 3 ln x3I minus ln x2 bracket close plus mu I. Ln yi minus ln x2i is equal to beta o plus beta 3 bracket open ln x3i minus ln x2i plus mu I, or ln y divided by x2i is equal to beta plus beta ln x3i divided by x2i plus mu I. Here y divided by x2i denotes output labor ratio and x3i divided by x2i denotes capital labor ratio. The validity of the restriction, we use the F-test. The statistic, which is equal to RSSR minus RSSUR, the whole divided by M, the whole over RSSUR divided by N minus K, which is equal to sigma hat squared R minus sigma hat squared UR divided by M, the whole divided by sigma hat squared UR divided by N minus K, which is equal to R squared UR minus R squared R divided by M, all over 1 minus r squared ur divided by n minus k, follows F distribution with m and n minus k degrees of freedom. Here sigma mu hat squared ur is equal to RSS of unrestricted regression and r squared ur are corresponding r squared values. Sigma u hat squared r is equal to RSS of restricted regression and r squared r are corresponding r squared values. Here sigma mu hat squared ur is equal to RSS of unrestricted regression. R squared ur are corresponding r squared values. Sigma mu hat squared r is equal to RSS of restricted regression. R squared R are corresponding R squared values. Note that sigma mu hat squared R is greater than equal to sigma mu hat squared UR. M denotes number of linear restrictions. In the example, it is 1. K denotes the number of parameters in unrestricted regression. N is the number of observations. After imposing constraints on the model, a residual sum of squares results that is not much higher than the unconstrained model's residual sum of squares. It would be concluded that restrictions were supported by the data. If the residual sum of squares increased considerably after the restrictions were imposed, it would be concluded that the restrictions were not supported by the data and the hypothesis would be rejected. Example, consider a Cobb-Douglas production function fitted to an economy's data for the period 1990 to 2009 with the following result. ln GDP hat is equal to minus 129.439208 plus 8.095468 ln labor T plus 0.253359 ln capital T. T is equal to minus 7.609275 and 7.644071 and 1.951656. P value is equal to 0.000001 and 0.000001 and 0.067654. Standard error is equal to 17.010715 and 1.059052 and 0.129817. R squared is equal to 0.978207. Star RSSUR is equal to 38.525827. Star SSEUR is equal to 0.858280. As the results show, output labor elasticity is about 8.10, output capital elasticity is around 0.25. Adding them, we get 8.36, suggesting that the economy was experiencing increasing returns to scale during the sample period. Now, our objective is to see if our finding is statistically different from 1. For the purpose, we impose the restriction of constant returns to scale and get the following results. ln GDP divided by labor hat T is equal to 3.785507 plus 1.190436 limit capital divided by labor T. T is equal to 6.845303 and 11.321751. P value is equal to 0.000002 and 0.000000. Standard error is equal to 0.553008 and 0.105146. R squared is equal to 0.876866. RSS hat R is equal to 8.169922. SSER hat is equal to 3.955770. Star UR is unrestricted regression. Hat is unrestricted regression. The dependent variables differ in both the regressions, so we use the F test. FCAL is equal to SSER minus SSEUR divided by A all over SSUR divided by N minus K, which is equal to 3.955770 minus 0.858280 divided by 1 all over 0.858280 divided by 17, which is equal to 3.60895. Here m is equal to 1 as there is one restriction and n minus k is 17 as we have 20 observations and 3 parameters. The computed f statistics is compared with the critical f values with m and n minus k degrees of freedom at the chosen level of significance. If we observe that the restricted least square is not significant as the computed f value is less than the critical f value, which is 4.45 at 5% level of significance, and thus we can conclude that the production function probably exhibited constant returns to scale during the sample period. Let us now summarize what we have learned in this module. Regression analysis involves prediction of average value of dependent variable on the basis of fixed values of the independent variable. A regression model in which more than one independent variable is used to predict the dependent variable is called a multiple regression model. A multiple regression model has more than one independent variable. The point estimate of a partial regression coefficient is estimated using the method of ordinary least square using the simple or the sample multiple regression function. A measure of goodness of fit for the estimated regression equation is the multiple coefficient of determination. The F test for a set of hypotheses is based on a comparison of the sum of squared errors from the original unrestricted multiple regression model to the sum of squared errors from a restricted regression model in which the null hypothesis is assumed to be true.